The James Webb Space Telescope has finally arrived at the Sun-Earth L2 point after a 1.5 million kilometer voyage. After the dramatic unfolding of the telescope, it's finally in its designated orbit. Webb had earlier spent the last 30 days gradually and carefully unfolding its sun shield and other important instruments. A mid-course correction burn, dubbed as MCC2, placed the James Webb in an orbit around L2. In fact, it sent it into a very huge orbit, more than double the size of the Moon's orbit around the Earth. Webb will take around 6 months to complete a single orbit around L2, and this initial phase will be totally packed with mirror alignments, phasing, sensor calibrations, moving target tracking tests, verifications, station maintaining maneuvers, and eventually the first science observations by the telescope. But what precisely makes the L2 so unique? I mean, it's simply a point in space, and an empty one at that. So how can Webb orbit something that does not exist? In this video, we will talk about how James Webb orbits around nothing. It is true that the L2 is empty, but circling empty spots in space is really rather common. That's because anytime two heavy entities circle one another, they both orbit a shared center of mass, or barycenter. If the objects are large enough, the center of mass will be somewhere in the middle. We only say the Moon circles the Earth because its center of mass is within the Earth. However, because Pluto and Charon have comparable masses, their barycenter is located somewhere in the space between them. So the idea that anything may circle an empty point in space isn't all that surprising. But it is a two-body system. It doesn't explain how Webb can orbit a location that isn't in the orbit of another two-body system. The good news is that we can deconstruct this problem and figure out what the L2 point is and how Webb can circle around it. In reality, numerous spacecraft have previously orbited L2, including NASA's WMAP satellite and ESA's Planck and Herschel observatories. And both Russia's Spektr RG and ESA's Gaia spacecraft are now circling there. So what is L2? What are Lagrange points, and why are they so helpful for James Webb? When you ask an astronomer about the orbit of the James Webb Space Telescope, they'll tell you something that sounds like it's straight out of a science fiction novel. The Webb will not orbit the Earth. Instead, we will launch it almost 1 million miles into space to a location known as L2. L2 is short for the second Lagrange point, a marvelous accident of gravity and orbital mechanics that serves as the ideal location for the Webb telescope in space. There are 5 Lagrange points, located where gravity from the Sun and Earth balances a satellite's orbital velocity. Placing a spacecraft at any one of these sites allows it to maintain a constant position relative to the Earth and Sun while using as little energy as possible for course adjustment. The acronym L2 may sound futuristic and intriguing, but it really celebrates a 1736 mathematician. The Lagrange points are named after Joseph Louis Lagrange, an Italian-born mathematician and astronomer. L2 is one of the 5 Lagrangian points that connect the Sun to the Earth. Actually, these 5 locations occur in the vicinity of any two-body system. Therefore, there are Lagrangian points for the Earth-Moon system, a set of points for the Sun-Jupiter system, and so on. If a third object is put at any of these sites, the gravitational forces of the two enormous bodies cooperate to keep the third object stable in relation to the others. The practical result is that the third body follows the system as it circles. As a result, the Sun-Earth L1 point is an excellent location for both Sun-facing missions such as the Solar Heliospheric Observatory and Earth-facing projects such as DSCOVR. Similarly, L2 is the location for astrophysics missions such as Gaia and Webb. Even while Earth circles the Sun, spacecraft at both places retain continual line-of-sight connection with Earth. Webb, on the other hand, places a premium on L2 because a single sun shield can block the heat of the Sun, Earth, and Moon. That's an ideal location for infrared astronomy. However, there are a few crucial limitations. For one thing, the third item must have a very, very little mass in comparison to the larger bodies. That obviously is not an issue. Webb's mass is insignificant in comparison to Earth, let alone the Sun. The other limitation is that the Lagrangian points, particularly the first 3, are better characterized as metastable. I want you to stop what you're doing and try something. Use your finger, touch all your teeth and gums. Wait for a few seconds, and smell your finger. Why does it smell so bad? It's because you never use the bass brushing technique. What's the bass brushing technique? I don't know either. If you don't know, keep watching. There are more than 200 billion bacteria in your mouth. The food particles will have some chemical reaction with this bacteria that generates a material called plaque. This plaque will erode your enamel and damage the nerves in your teeth. Don't think the bacteria will stop here. Some bacteria can get into your bloodstream and cause severe disease. If you don't want to experience the pain and waste thousands of dollars when you visit your dentist, I suggest you guys pay more attention to your brushing techniques. Think back. Are you just brushing your teeth unconsciously every morning? Do you brush your teeth more than 2 minutes? Have you used the bass brushing technique? Do you think you know how to brush, but in fact you never do it right? The Sonic electric toothbrush is made to solve these problems. Its brushing speed is 100 times faster than a manual brush. Research has shown that after 3 months of usage, the chance of bleeding and inflammation will be reduced 62%, and it will clear the dentin 38% better than a manual brush. I have been using an M-Teeth X5 series toothbrush for a month, and I do feel that my oral condition is much better. It has a lot of features compared to other Sonic electric toothbrushes. It comes with 3 modes. The mode I like the most is the clean mode. It has the highest frequency. Plus, this electric toothbrush will only cost you a third of a regular checkup at your dentist. M-Teeth is very confident of their product. They promised a 30-day free return and a free 1-year warranty. They're also offering a 20% discount coupon for fans of the channel. Guys, if you want to give them a try, please check the link and coupon down below. The X5 series, totally worth it. Imagine a flawlessly smooth and frictionless saddle to get a sense of what I mean. Consider attempting to balance a marble in the saddle's precise center. It is theoretically feasible, but it is incredibly difficult to do in practice. An object traveling perpendicular to the Sun-Earth line falls towards the center, which is similar to the L2 point. However, it then either falls toward or away from the Earth. If Webb slips away from Earth, it will be in serious jeopardy, since the only way to get it back is to turn around and push back. However, this will cause the telescope to rapidly warm up. The mission would be over when all of the parts expanded, glues and adhesives melted, and the mission would be done. That's a negative thing. Webb's thrusters are only on the observatory's warm, sun-facing side. This is due to the fact that hot thrusters would contaminate the cool telescope side with heat or rocket exhaust that would otherwise condense on the optics. This too would be bad for the Webb telescope. A safer approach for placing Webb is to place it very near to L2, but not quite at L2. As a result, Webb is never at risk of dropping below L2, where it cannot be retrieved. That's why the Ariane 5 launch was purposefully intended to slightly undershoot, allowing the spacecraft to do a sequence of mid-course correction burns. The first two, MCC-1A and MCC-1B, were carried out on the route to L2. However, coming even slightly short of L2 introduces a new issue. The Sun is permanently eclipsed by Earth at that distance. Webb is fueled by the Sun. It could now employ nuclear power, but that is both expensive and difficult to implement. Another issue is that Coriolis forces might lead to Webb to break free near L2. In other words, Webb would be trapped in a small orbit around L2 that would need even more engine fires. Oh, and the moon's gravity on Webb is still a thing, and it changes all the time as it circles Earth. These real-world problems can be handled by simply establishing a big orbit around L2. But how can you orbit something that doesn't exist? To understand this better, we need to take into account the various forces acting on Webb. If Webb were at L2, it would be subjected to gravitational pulls from both the Sun and Earth. Now that Webb is circling the Sun, we can think of a centrifugal force dragging Webb in the other direction. The amazing thing about L2 is that the centrifugal force is precisely balanced by the gravity of the Earth and the Sun at this distance. You may have heard that there is no such thing as a centrifugal force, which is right. But since we are dealing with a rotating non-inertial frame, centrifugal forces are still a handy means of summarizing all the real effects that are taking place. Also, to keep it simple, we won't take into account the effects by the gravitation of the moon. Now, if we move Webb up some distance away from L2 horizontally, let's call it L2 prime for our understanding, it will send it farther away from the Sun and its gravitational pull gets weaker. It's also no longer parallel with the sun's direction either. To compensate this, Webb is not totally placed at the L2 point as we mentioned earlier. It is near to the L2 so that it doesn't slip away into space. But there's another problem now. Webb might get pulled towards the Earth. However, when it approaches the Sun-Earth line, Earth's gravity becomes greater and it travels closer to Earth. We can't let it happen because the heat load would be too much for the sun shield to bear. We can, however, offset this downward force by pushing Webb sideways into a circular orbit, just like the one you can see in the image on the screen. This creates a fresh centrifugal force that balances the downward force of gravity on Earth. When combined with the sideways motion, Webb takes up a new circular halo orbit around L2'. That means Webb is simply being pulled by the y component of Earth's gravitational force. This explanation might seem a bit overwhelming at first, but it is a very oversimplified version. The actual calculations the scientists at NASA did is way too complicated, taking into account all kinds of forces. To make matters easier, Webb was not really launched to L2. It was instead launched to a location around the edge of L2. Webb performed its MCC-2 burn to settle into its orbit as it began to fall away, and is now into an orbit that is tilted by about 33 degrees. The orbit is also not exactly round, but rather has an elliptical form. As a result, the distance between Webb and the L2 point ranges between 250,000 and 832,000 kilometers. For comparison, the Moon's semi-major axis is around 400,000 kilometers. Therefore, Webb's orbit around L2 is massive. This big orbit was chosen because it makes it much easier to arrive at L2. The further something is from its orbital focus, the slower it moves and the less energy it takes to manipulate. Because of the wider orbit, Webb will never be in the shadow of the Earth or the Moon during its mission. Larger orbits, on the other hand, may allow stray light from the Earth or Moon to get through the sun shield and reach the primary or secondary mirrors. Furthermore, a larger orbit may limit the number of connection possibilities with the deep space network. As a result, Webb will have to vary its orientation during its orbit to keep stray light off the mirrors at all times, as well as plan the communication downlinks properly. Webb completes one orbit around L2 in around 6 months. Although it occasionally flies out a little bit past this point, the geometric center of the orbit remains the L2' point on Earth's side. Remember, we don't want that ball in the center of the saddle. As a result, Webb will perform tiny station-keeping burns every now and again to keep its orbit stable. Every year, missions like Gaia only require 3 to 4 of these burns. Webb, on the other hand, will require significantly more frequent burns for a variety of reasons. For one thing, its sun shield is constantly subjected to a torque caused by solar radiation pressure. By spinning up its response wheels, Webb can counteract this rotating force. However, because the solar radiation pressure is constant, the reaction wheels must spin faster with time. A station-keeping burn is eventually necessary to spin Webb back into position and allow the wheels to throttle down. Webb's orientation also shifts as it points from one location to the next. All of these movements significantly disrupt Webb's orbit, necessitating more station-keeping burns to sustain. That is why Webb does a burn once every 21 days. The flight dynamics team at NASA's Goddard Space Flight Center calculates the exact time and duration of such burns. So hats off to the scientists for doing such precise calculations and allowing us to look into the questions of our origins. So what did you learn about the orbit of James Webb? We tried to make this video and explanation as easy as possible. So make sure to subscribe to the channel because we're to come back in the future with more unusual discoveries like this. And share this with someone if you've learned something about space today and remain insanely curious. Let us know what you think in the comment section below.